Hello everyone, today we'll be discussing recurrence relations and how to solve them. So first of all, we'll start with with the basic introduction and some examples of recurrence relations. So basically recurrence relations represent a series of numbers and here the first few terms in the series are given explicitly and the rest of the terms are specified by a function on the terms preceding them. So recurrence relations are commonly used to define very complex series very simply in terms of a simple formula or something. Okay, so an example of recurrence relations is a Fibonacci series, which you may be familiar with. It is given by this formula t sub n is equal to t sub n minus 1 plus t sub n minus 2. So this means the n terms of the series is given by the n minus 1th term plus the n minus 2 term, and t1 is 0 and t2 is 1. So using this, we can expand the series to generate the first 5 6 terms here. So basically this means that the second term is given, the third term is given by t3 minus 1 t2 plus t1. Okay, so third term 1 is given by 1 plus 0, and similarly this 2 is given by 1 plus 1, 3 is given by 1 plus 2, 5 is given by 2 plus 3, 8 is given by 3 plus 5, and so on, right? So basically this very complicated series could be easily given by this definition, which would not be possible otherwise. Okay, so an example of how a recurrence relation arises is this Tower of Hanoi problem. So first I'll tell you what this problem is, and then I'll show you how the recurrence relation arises from this problem. So the goal here is that you're given these disks of different sizes, and they're given as in stacked order of disk 1 is bigger than disk 1 is smaller than disk 2, and so on. And your goal is to make this to basically move this whole pile from here to here. Okay, so you want the first disk here, you want the second disk to be here, and you want the third disk to go here, and so on. Okay, but there are some rules to this there are some rules you have to follow. So you can move only one disk at a time. You can place only a smaller disk on a larger one and not vice versa, and you can only move the topmost disk of any stack. Okay, so basically I can move the first disk to some column, but I could not move the second disk here in one step, right? So if we only had two disks to move, then this would be very simple, because we will first move this topmost disk to another stack. We'll move uh, the bottom disk to the third one. We'll move the middle disk to the top of the bottom disk. So we move the whole stack from the first to the third, right? And we only had to use three moves here. Okay, so this gets a bit tougher, but not that tough. If you have two disks, here you first move this first disk to the third thing, you move the second disk to the second thing, and then you recreate the first two uh, first two disks on the second stack, and then you move the third disk to the third stack. You move the and then you basically move this stack of two disks to the back to the third stack, and you have the whole stack on the third stack. Okay, so now a question is, how would you make a general program to move this whole like this is an example of how you move four disks. So you can see how this is done, right? So the essential thing to note is what we are doing is basically we are creating the whole stack except the top disks on the middle column ones. Okay, and that's what I will show right now. Okay, so if you had a program which could by itself move three disks to from one pile to another, then we can easily extend it to 4 disks, right? So suppose magically we made these 3 disks go to the second pile. Then we have to, then it's very simple problem. We just move the largest disk to the third pile, and we again use the program to move the 3 disks to the third pile, okay? And so if the program to move 3 disks took 7 steps, then we use 7 steps here, one step then, and then 7 steps more, so we took 15 steps total, right? So this recursion is true for any n, okay? So for any n, I can move this stack to this pile, then I can move this to this big disk to the third pile, and then I can move this stack back to the this pile, and this would solve the problem which we wanted to solve, right? So this is what is shown here. So we move the first disk, so we basically take 2 times the time taken to move the n minus 1th pile to another stick, and we one more step, okay? Total number of steps is 2r n minus 1 plus 1, okay? This is the whole program which solves this problem for any n, okay? So now we'll show you, now as we have shown that this is the amount of time taken for solving the Tower of Hanoi problem for n disks. So it's given by 2 times time taken for the n minus 1th problem plus 1, and the time taken to solve to just move one disk from, if you had a problem with only one disk, then you just need one step, which is very obvious, right? So this is an example of how a recurrence can arise from a very complicated problem, and how you can, and later we'll show you how to solve this kind of recurrence to get an explicit formula for the amount of time taken by this algorithm, because we might need that, right? We might need to find out how much time our program takes on an input of, say, 120 disks, and we don't want to again and again plug values into this expression to find out the value. So we need an explicit formula, and that's called solving the recurrence, okay? So next I'll show you how we verify whether a solution that we guessed is accurate or not. So given a recurrent solution and a guess for its explicit solution, we often want to prove that the guess solution is the correct one. This is a very commonly used technique because in recursion, because in general the coming up of the answer is more complex than finding out whether this answer is the correct one or not, okay? So a very popular method is to draw a recursion tree and guess the explicit formula from the number of leaves which we are producing at every step, and the number of processing time needed for every node of the tree, okay? And the way we verify a solution to a recursion is using induction. Mathematical induction is the technique used, and it is a very deductive and simple argument, which I'll give a demo next time. So this is the general algorithm for the verification process, very basic induction argument. So first of all, you show that this formula works for the base cases of the recursion, which will be given to you. So for example, maybe your base case is just that the first term is given to be something, so you just have to show that the formula that you have guessed, f1, is equal to the first term of the recurrence, okay? Then you can assume that the ta equal to fa for all a less than k for some arbitrary k, right? Then you will use this relation, this ta equal to fa, to prove that tk equal to fk2, okay? And you can use all the k minus 1 all the k minus 1 equations that you have here. For example, you have tk minus 1 equal to fk minus 1, tk minus 2 equal to fk minus 2, all the way up to t1 equal to f1, and you can use all of them to prove this thing, okay? And then you can easily say that by strong induction on n, we have tn equal to fn for all values of n, okay? So this is what we'll use, and I'll show you a demo next. So so this is the recurrence which arose from the Tower of Hanoi problem. Tn equal to 2tn minus 1 plus 1, 2 times the amount of time taken to move the stack of n minus 1 disks, and 1 move for the nth disk, right? Example. So 2 times 1 time this, then this, then this again. So 2 times this plus 1. Okay. So suppose we guess arbitrarily that that fn is given by 2 to the power n minus 1. Okay, and we'll show you how to come up with this guess later, but for now just assume that we somehow came up with this, and we want to show that this is the true solution to this equation, right? So for the base case, we have to prove that f1 is t1. So f1 is 2 minus 1 equal to 1 is t1. So this is very obvious, right? Next step is a crucial one. Here we give an inductive argument. So suppose that t equal to fa equal to 2 to the a minus 1 for all a less than k. Now now from the recurrence we know that tk is equal to 2 times tk minus 1 plus 1. But since we have already assumed that tk minus 1 equal to fk minus 1, so we can put tk minus 1 equal to 2 to the k minus 1 minus 1 in place of tk minus 1. So we put that here, and then we just expand this whole equation, and we get 2 to the k minus 1, okay, which is equal to fk. So we showed that if ta equal to fa for all a less than k, then tk equal to fk. So and then by strong induction, because we have a base case and we have an inductive argument, so we can say that this guess was the correct guess, and fn equal to 2 to the n minus 1 gives the n term of the recurrence all the time. Okay. So next we show you how to solve recurrences in general. Okay. So this is how you first come up with the solutions to many recurrence problems from just observing their terms. So this is a very simple recurrence. Ak equal to ak minus 1 plus 2. Okay, and the first term is 1. So basically you're adding 2 to every step. Okay, so you can see we get 2, then we get 1, then we'll get 3, then we'll get 5, then we'll get 7, and so on, right? So here we just identify the pattern. So it's very clear that for the nth step we are adding 4 times n to the base case, right? So ak is given by 2 times k plus 1, and this can be verified by induction as we have shown earlier. So now we'll show you how to come up with the guess for the Hanoi solution that we did. So we expand some of the terms of the equation. So a2 is given by 2 times 2 times a1 plus 1, 3. a3 is given by 2 times a2 plus 1 equal to 7, and so on. Okay. So how would you come up with this guess, ak equal to 2 to the k minus 1? So basically you assume that, so you can kind of see that every step we are multiplying the previous value by 2 and then adding 1. So at the kth step we'll have multiplied by 2 k times. Okay, actually k minus 1 time. Okay, okay, actually sorry, k times only, because here you multiply 1 time, 2 time, 3 time, right? So every step you're multiplying by 2 and you're adding something. So you can see that the general thing will be 2 to the k minus 1. So 2 to the 6 is 64, minus 1 is 63. 2 to the 5 is 32, minus 1 is 31, and so on, right? And then as we have shown earlier, then this can be verified easily by induction, by an induction argument. Okay. So now we'll show you what are second order recurrence relations. So second order recurrence relations are a general form of recurrence relation where the k term is given by a combination of the k minus 1th term and the k minus 2nd term. That means that the any term is given by a linear combination of the two terms preceding it. Okay, and a and b are real numbers. B is not equal to 0, and you can see that if capital A equal to B equal to 1, then AK is just given by AK minus 1 plus AK minus 2, which is just the Fibonacci series. Okay, so for a general so now we show that if you have a general sequence, how would you get the solution to this general sequence, right? So these solutions to such kind of equations are of the form AK equal to T to the K. So this is actually this actually comes from practice and some solving some linear equations. So suppose that we guess that the solution to this equation is the K term is given by T to the K. Then we can put this kind of thing in this equation and we can get a quadratic equation in terms of T. Okay. So for a given recurrence relation with capital A and capital B, this quadratic equation will determine the solution to this recurrence. So here you have an example. Suppose suppose this series is the one that we need to find the solution of. So like the previous slide, we'll have the solution will be of the form t square minus at plus minus b. So t square minus a is 1 and b is 2. So t square minus t minus 2, okay, equal to 0. So if you solve this quadratic equation, you'll get t equal to 2 and t equal to minus 1. Okay. So either the solution will be of the form 1, 2, 4, 8, 16, 32, 64, or the solution will be of the form 1, minus 1, 1, minus 1, 1, kind of like that. Okay, so you can verify that this satisfies this. For example, the third term, 1, is given by minus 1 plus 2 times the first term, which is 2. So 1 is minus 1 plus 2, which is true, right? So now you can also say that these are not the only solutions to this equation, because these solutions are also satisfy this equation. So example, 5 is equal to 1 plus 2 times 2, 1 plus 4, right? 7 equal to 2 plus 5, 17 equal to 10 plus 7, 31 equal to 14 plus 17, right? So how do you obtain such kind of solutions? So if one series and two series are solutions to a general form to a general series of the form ak equal to ak minus 1 plus bk minus 2, then any linear combination of these two sequences will also be a solution to this series. Okay, this is very easy to check. You can just see that because all these three things are linear, so a linear combination of the input will also equal the linear combination of the output, right? So this theorem says that if this recurrence if this recurrence is given by ak equal to a k minus 1 plus b a k minus 2, and this quadratic equation has two roots, then any solution an to this recurrence is given by a linear combination of the two polynomials r to the n and s to the n, right? So for example, for the previous solution, for the previous equation, r to the n would be 2 to the n and s to the n will be minus 1 to the n, right? So if you're given a0 and a1, then you'll have two unknowns and two equations. Two knowns, a0 and a1 would be known, and you'll have two equations to find A0 and A1 using C and D, right? So now we solve the Fibonacci series by the methods we have developed so far. So for the Fibonacci series, we've seen that A0 and A1 are given by 0 and 1, and the series itself is given by ak equal to ak minus 1 plus ak minus 2. So the quadratic equation is t square minus t minus 1 equal to 0, and the roots are 1 plus root 5 by 2 and 1 minus root 5 by 2. Okay, so by the previous theorem, we'll have that any solution an will be given by c times this and d times this, right? Now we want to find c and d first, but and we'll have a0, the value of a0 and a1 to find c and d. Okay, so a0 is 0, we put a0 here, which is 0, and we can put n equal to 0 in place of n. So we'll have 0 equal to c plus d and 1 equal to c 1 plus root 5 by 2 to the power 1, which is just that and this. So to solve, you can solve this and you can get c equal to 1 by root 5, d equal to minus 1 by root 5. Okay. So basically you have that this equation basically is the closed form solution to the Fibonacci equation. This particular equation is the closed form solution to the Fibonacci equation. So it's very surprising, but for example 0 1 2 0 1 1 2 3. So if you put n equal to say 5 here, so if you put n equal to 5 here, you will get 3, right? So this is very good for example, if you want to find the 1000th Fibonacci number, but you don't want to, for example, first go to and find the 999th Fibonacci number, then find the 997th Fibonacci number. So you don't want to go down the recursion tree, you just want to find the nth number. So here it's very useful, right? So what happens if the quadratic equation that we found only has one root? So we know that r, so suppose that r is the root of this quadratic equation, then we know that r to the n is one solution to this recurrence relation. 1 r square r cube r4 satisfies this recurrence relation. Now the question is, are there other solutions? Yeah. So in the case where r is the single root of the equation, you'll find that this 0 r 2r square also satisfies the recurrence relation. Okay, and here is a very basic proof of this equation. So we assume that a is 2r and b is minus r square, and we say that so we show that this satisfies this. So this term satisfies leads to this solution, right? So this is this basically says that if you have only one root r, then there are two equations, r to the n and n r to the n, and any solution will be given by a linear combination of this plus this, right? So so if you have ever done differential calculus and solved differential equations, then you would recognize the similarity with the quadratic differential equations. They also have some stuff like this, right? Now we come to the topic of generating functions, which are often used for solving recurrence relations. So what the basic concept is that for any sequence of numbers which is the recurrence relation which the recurrence relation satisfies, we first find a function, and this function is a polynomial. So for every sequence we associate a function, and this is a one-to-one association, and this function is a polynomial. And by mapping every sequence of numbers to a function, you can you can easily find the explicit formula for the number sequence. So suppose G0, G1, G2, G3 is the sequence. Then the generating function is defined to be G0 plus G1x plus G2x squared plus G3x cubed, and so on. So this sequence and this function, and there is a correspondence between them. So given any series, I can give you a function, and given any function, I can give you the series corresponding to that function, right? So for example, say 1, 2, 3, 4, etc. would be given by 1 plus 2x plus 3x squared plus 4x cubed, and so on, right? And there are some examples here. So for example, if you have this series, then it will be given by 0 plus 0x plus 0x cubed, which is a 0, right? If you have a series of this form, then it will be represented by 1 plus 0x plus 0 cubed. And these are some basic examples. So you can guess a basic thing that the ith term of the sequence is the coefficient of x to the I here. So the third term in the sequence is the coefficient of x to the cube, and here we say the first term of this sequence is basically the 0th term. Okay, this is the convention. So this is an example of the geometric series, which is just 1 plus x squared. So this will correspond to the basic series 1, 1, 1, and so on. And we do some basic manipulations on this. We do some basic manipulations on the sequence. We multiply it by x, and we get this, and then we subtract gn from gn minus subtract x times gn from this, and all of these terms cancel out. Okay, and we'll get just 1, right? So this whole series has a closed form representation 1 over 1 minus x. So and you may have seen the Taylor expansion of this. 1 over 1 minus x is given by 1 plus x squared, and this is how you prove that, right? Similarly, 1 minus 1, 1 minus 1. This series corresponds to this function, and this basically has a closed form representation 1 over 1 plus x. And this series corresponds to this function, and this function can also be written as this, right? So these are very common stuff. So a lot of manipulations on sequences can be easily represented by manipulations on the generating functions, and this is why this is the basic reason why generating functions are used, right? So to get new sequences from known sequences, we can do manipulations on the generating function of the known sequences, right? And we can get new sequences ka closed form representation. So for example, multiplying any generating function by 2 basically multiplies the whole sequence by 2. So this is the sequence. If I multiply all the terms by 2, then we'll get 2, 0, 2, 0, and so on. And the generating function for this sequence will be this, right? And the closed form for this can just be found by multiplying this by 2. So we found the closed form expression for this generating function expression for this sequence easily, right? Similarly, we can add generating functions to find the generating function of another sequence, right? So the generating function of this sequence can also be found by adding these two generating functions. Differentiating can also, so for example, the generating function of 1, 2, 3, 4, etc. is this, and it can be found by differentiating this series generating function. And the derivative of this is just 1 plus 2x plus 3x squared, and so on, right? So now we show you how to solve some recurrences using generating functions. So this is a real world example of a rabbit population where every mature rabbit pair reproduces every month, and rabbits mature after every month, and we start with a newborn pair. Okay, so if you see how this is formulated, you'll see that this is this basically result in the same series as the Fibonacci series, right? So so the number of pair after n months is given by the sum of pairs after n minus 1 month, and the sum of pairs after n minus 2 months. So so this is the Fibonacci series, and we want to find a generating function for this sequence. Okay, and we want to find a closed form for the generating function. So what we do is we basically find we assume that Rx is the generating function for the number of rabbits after x months, and we compute Rx minus x square Rx, and we'll find out that this function here the many terms cancel out, and this function basically reduces to x. And so the closed form for Rx is given by x over 1 minus x square. Now the important question is, what is the closed form for Rn? So here we use the method of like factoring to find of partial factors to factor out this expression in terms of a and b, and we know that this basically corresponds to this series and this corresponds to this series. Okay, and we want the coefficient of x to the n in Rx, because this will correspond to the an, the n term of the Fibonacci series. Okay, so this will be given by a times this thing plus b times this thing. So the coefficient of x to the n will be a times alpha to the n plus b times beta to the n. Okay, and using the first two terms, because we'll given a0 and a1, we can find out that alpha is 1 by 1 plus root 5 by 2, beta is this, and a you can find capital A, capital B from these. Okay, and so a times alpha to the n plus b times beta to the n is given by 1 over root 5, 1 plus root 5 by 2 to the n minus 1 by root 5, 1 minus root 5 by 2 to the n. Okay, so this is the same as the closed form we found earlier. So you can see that both methods gave us the same answer, but this method was a bit simpler. We didn't have to guess that the solution would be of the form tk. This was self-explanatory, right? So thank you, and this was our slide. Thank you, and I'm Madhur.